This is Bob McFetrich with Beckwith Electric. I'd like to welcome you to our M-6200 training sessions, and in this session we will be discussing voltage reduction. And again, just to reiterate, the version of TapTalk that will be shown during this session is version 020601, and the version and firmware of control that supports these features will be version 010500. So, the purpose of voltage reduction is ultimately to reduce load. And the closer to power factor we are, the more load we can reduce as we reduce the voltage. This slide shows a study that I believe was done by EPRI a few years back, and it indicated that for every 4% of voltage drop, you'd get about 3% of load reduction at unity power factor, and that would go down to about 2% of load reduction if the power factor were 0.9, lagging. So, the goal of voltage reduction is to reduce load, either full-time or on a demand basis when needed. And with that, there are multiple ways that we can institute voltage reduction on an M-6200A. First of all, we have three different programmable levels, level 1, level 2, and level 3. And each of these levels can be set for any percentage from 0 to 10%. There is an LED on the front of the M-6200A for voltage reduction, and it'll be off if we're not in reduction, and it'll be on if we are, but it'll blink, and the rate of blinking will determine which of the three levels. So for level 1, it'll be on solid, then blink once, then on solid, blink once. Level 2, it'll be on solid, then blink twice in a row, then solid. And level 3 would be solid, blink 3 times in a row, and then solid. Now, we can place reduction, the control in reduction, from a front button on the control locally, or we can do it via our SCADA interface, via DMP commands, or via TapTalk, either locally or remotely, or a final way is via hardware, where we have two voltage reduction digital inputs available on the control, and between those two we can get 3 levels of reduction. So looking at the control, there is the voltage reduction LED, and there is the voltage reduction push button. Now, to access voltage reduction locally, we would have to be on the main screen on the HMI. If we're not on the main screen, we would hit the exit button until we got back to the main screen. Once on the main screen, if we hit the voltage reduction button, we will be prompted as to what stage we want to enter, and then if we hit the enter button after selecting a stage, we would see the voltage reduction light go on. We would be in reduction at that percentage, and it would stay on until we left the reduction. A second hardware way would be the two voltage reduction inputs we had talked about. So on TB12 we have input number 2, and then down on TB17 we have input number 1. Now both of these would have to be wetted, so they're contacts wetted with our 12 volt power supply, which would be off of TB14. So if we ran TB14 to one side of two contacts on an RTU and brought the other sides back to TB17 and TB12, we could then issue latching commands to those outputs on the RTU and have the RTU drive reduction that way. So if we have an older legacy RTU that cannot support pulling the control directly via DMP, we can do a hardwire approach using those two external contacts. But one has to remember that voltage reduction does not reduce the voltage. It actually reduces the band center. And so we're going to take look at a couple examples and see how that affects what's going on. So in the first example, we're going to start with a band center of 122 and a bandwidth of 3. And we're going to request a 2% reduction. Now, when we request a 2% reduction, all we're doing is telling the control to use a new band center. So it's going to take the existing band center of 122 with a bandwidth of 3, and it's going to multiply and reduce that band center by 2%, which would then change it to 119.6. And at 119.6, we're still going to have the same 3-volt bandwidth. So basically what we've done is we've changed the band center from 122 to 119.6, and that's all we've done. And we can see that if the voltage was in this area right in here prior to issuing the command, we will not even do a lower after going into reduction, because the voltage would still be in band on its new band. So we just went from being on the low side of the existing band, or the original band, to now being on the high side of the new band. So this demonstrates that you can enter voltage reduction, and if everything is set accordingly, you may not even get a lower. You may not lower the voltage at all. Now, taking the same example, but changing it to a 3% reduction instead of 2%, we calculate a new band of 118.3, still using our same 3-volt bandwidth. We can see that there's no overlap. So the high band is below the old low band. This guarantees that no matter what the voltage was prior, we will definitely be forced to take a lower to get into the new band. But we'll also notice that we still won't get the full 3% that we've requested. So if we started at 120.7, when we issue our first lower 3/4 of a volt per tap, that still puts us right above the band. So we're going to have to take a second tap, and we'll finish up at about 119.2. So for this 3% reduction, we started at 120.7 and we finish at 119.2. Now, what if we were to do a 3%, but instead of just doing a 3%, we will start with a 6%, and then we will follow it by a 3%. So ultimately, we're going to finish up at 3%, but instead of just starting with 3, we're going to start with 6%. Well, if we do a 6% reduction, our new band center becomes 114.7, and starting the voltage out here and going 3/4 of a volt per tap, ultimately we have to finish up to get lower than 116.2, and we'll finish up at 115.5. Then if we do a level 3, a level 3 does 3% of the original band, which then would actually shift the band back up to 118.3. You can see now that we're actually starting out below the band and having to come up. And if we come up one tap, we will finish at 117, and that will be slightly above the 116.8, and we'll be back in band. So interestingly enough, if we just started with level 3, we were coming down, so we finished up at 119.2 because we're entering from the top of the band. If we start with the levels 2, 3, 6%, and then come back to level 1, 3%, now we're coming in from the bottom band, so to get back in the band, we're entering at the bottom, and it's 117. So even though it's a net 3% reduction in either case, we've picked up an additional 2.2 volts from 119.2 to 117 in reduction by going to the lower step first. So with this in mind, it's important to realize that with voltage reduction, you're never going to get what you request. And the amount you actually do get is going to be determined by the size of your bandwidth. So the larger the bandwidth, the less percentage you're going to get, because the quicker you're going to come into the new band. If I had a 2-volt bandwidth, then this would be 119.3. And where we were 119.2, we would still be in band. So in that particular case, it still would not have helped us. But if we went to 1.5 volt bandwidth, then it would have had to take another tap to get into band. So the wider the bandwidth, in normal modes is good because it reduces operations, but when you're in reduction, the wider bandwidth actually reduces the percentage that you're going to get, and therefore you may want to do one of two things. Either ask for a larger percentage than you need, knowing that you're not going to get everything you ask for, or you can send a command to reduce the bandwidth just prior to reduction, so that when you do go into reduction, the bandwidth will not be eating up as much. One last thing to remember on voltage reduction is the block lower setting, as we talked about in the blocking session, will block voltage reduction. So if we set our block lower at 118, but we want after voltage reduction to be down around 116, that's not going to happen. So a lot of utilities misset the block lower by looking at the lowest voltage they would normally want to have on a circuit instead of what the lowest voltage they want in an emergency condition after going into reduction. So to calculate the block lower setting, one really needs to go into the highest percentage reduction, and then from that figure out what the voltage would be to stay in band, and then you would want your block lower to be set on that particular low edge of the band. So in this case, if I were wanting to actually have this as my lowest reduction, what I'm saying is I'm saying it's okay for the voltage to be 114.4, so I would want my block lower to be set at 114.4 or slightly lower and not the 118, because in this case we will start the reduction coming down, but as soon as we hit 118 we're going to hit the block, and that will stop any additional lowers. So again, we have three different for the settings on voltage reduction. They're under the set points window, and you can see first of all we have to enable it if we want to use reduction, and then we can assign different percentages for each of the three steps, and those percentages can go from 0 to 10 in 0.1% increments. So those would be the valid settings for the reduction, and again we also need to coordinate that with the block lower setting to verify that we're going to get the full reduction desired. Now, when you enter reduction, if the LTC or regulator, in this case single phase regulator, needs to tap, it will be immediate. So this is the second time where you will have no time delay before doing an operation. The first one was the force lower we talked about in the blocking session for first house protection, where if the voltage gets too high, you immediately send a lower. The second case is in voltage reduction. If voltage reduction is instituted and the voltage needs to be lowered, there will be no time delay. Now, if we're going to do reduction from SCADA, we want to make sure that there's a means to turn it off if SCADA communications goes down after issuing it. So if we issue a voltage reduction command for level 2 to SCADA, and we want to come out of reduction, but we cannot communicate to that control, then we're going to have to send somebody out locally to bring it out of reduction. So one thing we've done is we've added a timer, and the way this timer works is if you set it to any value other than 0, then what's going to happen is once SCADA issues a voltage reduction command, the control will stay in reduction for that amount of time and then immediately come out of reduction, even if you're still communicating. So if you're still communicating and you want it to stay in reduction longer, you have to resend that time. So for instance, if it's set for 15 minutes, the first time I enter reduction, it'll start the timer counting down. If I do not send another reduction command to keep it in reduction before the 15 minutes expires, it will automatically come out of reduction on its own. If I want it to stay in reduction for an additional 15 minutes, I'll have to reissue that command just prior to the timer expiring and get another 15 minutes. Also, we can see under the input selection screen that second VR reduction input can be used for hardware reduction or can be used as an auxiliary DNP input. So we have cases where customers on bus regulators have a temperature alarm contact that they want to bring back into SCADA. Well, if you're using the voltage reduction via communications, you don't need the hardware inputs, and so this is a way of freeing up one of those hardware inputs so that it's not tied to voltage reduction. So if I were to select this as an auxiliary input, now if VR2 is high, that is not going to trigger a voltage reduction, and we should not see the voltage reduction light come on in the front of the control if that VR2 input is active. So it's a way of using one of the two voltage reduction hardware inputs for other purposes, but still allowing you to do voltage reduction via communications. Now, we're going to cover the DNP mapping in a completely different session, but we wanted to go through some of the points that are available for monitoring and controlling voltage reduction. First of all, our binary inputs are status points. So the first two we see here are the two hardware contacts. And then the next three would be the software if we were doing from voltage reduction from SCADA. And the last would be via the front panel. So if this was a 1, it would tell me the voltage reduction is being applied via the front panel. I wouldn't know necessarily what level, but I know it was applied via the front panel. A 0, and I know it's not being applied via the front panel. Likewise, these two hardware inputs would tell me whether the voltage reduction is being applied via the hardware inputs. And finally, these three would be a 1 if via SCADA it was in voltage reduction via any of the three steps. So those are the binary inputs that we would want to monitor typically with voltage reduction. Next will be the binary outputs. So first of all, we can have a command down at the bottom, a latch on, latch off, to enable voltage reduction. So if we send a latch on, it enables it, a latch off disables it. Then we have latch on, latch offs for each of the three individual stages. And a latch on places that in voltage reduction, and a latch off takes it out of voltage reduction. Now, as an aside, if we were in level 1 reduction and we sent a latch on command for level 2, that would take it out of level 1 and place it in level 2. So when you're going from one level to another, you don't have to come out of the first level to enter the second. But if you just want to come out, then you would have to send a latch off. So for instance, if I wanted to do like we saw before and start with a level 2 and then go to a level 1, I can send a latch on to the level 2. Then I would say after 30 seconds or so, giving the regulator time to settle down into its new voltage, then I could follow that with a step latch on level 1. That will automatically bring me out of 2 and into 1. And then when I wanted to leave altogether, I would have to do a latch off on level 1. So that is how the digital outputs or the binary outputs work. We also have analog outputs, which are basically the way we can change the percentages for each of the three levels. So I can write a different percentage to each of the three levels. Now, with all of our analog outputs, if there's a decimal point involved, we do a multiply by 10. So in this case, the percentages are allowed to be from 0.0 to 10.0. So we allow 1 decimal point resolution, so we have to multiply by 10. So for instance, if I wanted a 2.5% reduction, I would write a value of 25 into that particular setting, and then the control, when it received it, would divide it by 10 and come up with the 2.5%. And finally, we have an analog input that shows you when it's in reduction what percentage is being applied. And from that, you can know what level. So if I were in level 2 and level 2 was set to 5%, I would be getting back the value of 50 on this particular point and do a divide by 10, and it would show me that there's currently a 5% reduction being applied. So I hope this has been beneficial and give you a little better insight into how voltage reduction works. We are currently doing a major revamp of voltage reduction for the next release of firmware, so stay tuned for some exciting things where we're going to be a little bit more smarter in the way we do voltage reduction. But this is the way it's currently operating in this version of firmware, and we thank you for your time. And if you have any comments, questions, concerns, feel free to submit them via the web portal. Thank you, and have a blessed day.